Welcome to the Sleepy Brain Facts channel. Tonight, you embark on a journey into the enchanting realm of electricity. This force, so familiar that you often overlook it, is both ancient and mysterious. Having shaped the universe since its inception, electricity serves as the quiet heartbeat within every storm cloud, the shimmering essence behind each thought, and the delicate thread that connects matter, life, and light. As you settle in, picture tracing this invisible power from the heart of a thunderstorm to the depths of your mind. Imagine the sparks of newborn stars and the soft glow of a lantern in the dark. Together, we will explore how electricity moves, transforms, and reveals the hidden workings of nature, carrying wonder in every direction it flows. If you find joy in these tranquil explorations, I gently encourage you to like, subscribe, or share your thoughts below. Your support helps others discover this space, one sleepy soul at a time. Now, take a deep breath. Allow your eyes to grow heavy and your mind to relax. Let's begin. Electricity is the silent architecture of every living cell. Within every organism, from the tiniest microbe to the most intricate human being, electricity provides an invisible framework that enables life to function with remarkable precision. Every cell you encounter maintains a delicate balance of charged particles across its membrane. This creates tiny voltage differences, acting as the language of biology. These charges play a crucial role in determining when nutrients enter, waste leaves, and chemical reactions ignite. Imagine ion channels as microscopic gateways that open and close, responding to subtle electrical cues. They guide the cell through each step of its existence. Even the simplest life forms depend on these currents to sense their surroundings, move, and adapt. Without this constant flow of charge, the instructions encoded in DNA would remain silent. The machinery that reads and interprets these instructions relies on electrical gradients. In this sense, electricity forms a quiet yet essential backbone of life. It is a continuous whisper within every living cell, shaping growth, healing, movement, and awareness. Consider the phenomenon of lightning, the Earth's most ancient form of electrical power. Long before humans harnessed electricity, our planet showcased breathtaking displays of energy through lightning. These massive discharges occur when storm clouds gather charge, often resulting from countless collisions between ice particles that separate positive and negative regions within the cloud. Take a moment to reflect on the incredible balance of energy that sustains life and the natural wonders that remind us of its power. Imagine a moment when the electric field intensifies, reaching a threshold where the atmosphere can no longer hold back. In that instant, a brilliant flash of light streaks across the sky, reshaping the very air around it. This burst of energy heats the atmosphere to astonishing temperatures, expanding so violently that it produces the resonant sound of thunder, marking the event with its unmistakable signature. Lightning plays a crucial role in our planet's balance, regenerating essential compounds in the atmosphere. It has the power to strike far from the storm that birthed it, branching out unpredictably across the landscape. For countless generations, lightning has evoked both fear and wonder, serving as a reminder of nature's incredible electrical forces. Just as lightning illuminates the world, your body generates its own electrical messages every moment. Each sensation you experience and every movement you make begins as an electrical signal, traveling swiftly through your nerves. These signals arise from changes in the balance of ions surrounding nerve cells, enabling each cell to fire rapid electrical impulses known as action potentials. When something brushes against your skin, tiny receptors spring into action, converting that physical sensation into an electrical wave. This wave races toward your spine and brain, carrying vital information about your environment. It's a remarkable journey, one that connects you to the world in profound ways. As you reflect on this, consider how these invisible forces shape your experiences. Would you like to delve deeper into this fascinating interplay of electricity and life? Imagine a world where messages flow purely as electrical signals. They journey to the end of a nerve, where they transform into chemical signals that leap across tiny gaps between cells, igniting new electrical pulses on the other side. This relay is endless, creating a vibrant network that keeps you connected to your surroundings and enables instantaneous reactions to the world around you. Even during sleep, your body tirelessly generates these signals, regulating essential functions like breathing and heart rhythm. This happens without you even realizing it. Within your brain, thoughts emerge from cascading electrical storms. Every idea, memory, emotion, and decision is shaped by billions of neurons that weave intricate patterns of electrical activity. These patterns are formed when electrically charged ions move across neuronal membranes. This movement allows each cell to fire rapid pulses that influence its neighbors. Your brain is a complex tapestry of branching connections. Each electrical spike travels through this network like a spark racing across a dense forest of pathways. When groups of neurons synchronize their firing, they create brainwaves, large-scale electrical patterns that reveal your state of consciousness. Take a moment to reflect on this incredible process. Isn't it fascinating how your brain operates, even when you're unaware? As you take a moment to reflect, you might notice how calmness, focused attention, dreaming, and deep sleep each exhibit their own unique patterns. What's truly fascinating is that your brain continuously reshapes these patterns as you learn and grow from your experiences. Synapses in your brain strengthen or weaken based on electrical activity, allowing memories to form through repeated patterns. In this way, your inner world of thoughts and imagination emerges from the silent electrical storms that flash within your mind. Consider the incredible navigation abilities of birds. They harness the Earth's natural electric signals to travel vast distances. Many migratory birds have the extraordinary ability to sense faint electrical cues, guiding them across continents and oceans. The surface of our planet carries a natural electric gradient, a result of the interplay between the ground and the atmosphere. Birds seem to detect changes in this field, integrating it into their navigational toolkit, which also includes magnetic sensing, the position of the sun, and environmental landmarks. Research indicates that certain receptors near a bird's beak respond to even the slightest shifts in electric potential. This awareness helps them gauge altitude, detect weather changes, and sense approaching storms. Such sensitivity becomes invaluable during long migrations, especially when visibility is low and magnetic signals can be unpredictable. As you ponder this remarkable connection between nature and your own mind, you might feel inspired to explore further or simply embrace the calm around you. Imagine a world where birds navigate their flight paths using a blend of natural cues, guided by an almost unseen electrical awareness. This remarkable ability reveals that many animals perceive forces in their environment that often escape human notice. Their long journeys become not just feats of endurance, but also triumphs of sensory sophistication. Now, consider the trees around you. They communicate through an intricate underground network, sharing electrical warnings via their roots. Beneath the forest floor lies a hidden realm, where trees can send subtle electrical signals through interconnected root systems and the shared soil. When a tree faces stress, perhaps from drought or insect damage, its internal electrical balance shifts. These changes can ripple through the roots, alerting neighboring trees to impending threats. Research suggests that these signals can influence how much water nearby trees absorb or how quickly they release defensive chemicals. The soil, abundant with minerals and moisture, serves as a natural conductor, allowing these electrical pulses to travel surprising distances. Moreover, fungal networks entwined with the roots may enhance or spread these signals even further, creating a complex electrical ecosystem that unites individual trees into a cooperative whole. Isn't it fascinating to think about the silent communication that thrives beneath our feet? This hidden world invites you to reflect on the connections that exist all around us. Feel free to continue exploring or take a moment to rest and absorb these thoughts. Imagine a world where trees are not just solitary beings, but part of a vast interconnected network. Underground, they communicate with each other, sharing vital information that helps them adapt to changing conditions. This remarkable ability fosters resilience and unity, sustaining entire ecosystems. Now, let's turn our gaze skyward. The aurora, that breathtaking natural light display, glows brightly because of solar electricity interacting with Earth's magnetic shield. High above, charged particles from the sun travel along magnetic field lines, colliding with atoms in the upper atmosphere. This cosmic dance is known as the solar wind, carrying electrical energy across immense distances. When these particles reach the magnetic poles, they spiral downwards, energizing atmospheric gases. This interaction creates shimmering lights in hues of green, red, and violet. The process is a beautiful blend of electrical and magnetic forces, illustrating the relationship between the sun's energy and the protective shield surrounding our planet. As solar activity fluctuates, these displays can become even more vibrant, transforming the night sky into a canvas of rippling luminosity. The aurora serves as a visual representation of Earth's electrical connection to the cosmos, revealing forces that often remain invisible to us. Each glow you see is a testament to a charged particle completing its journey from the sun to our atmosphere. Isn't it fascinating how these natural phenomena remind us of the intricate web of life and energy that surrounds us? If you feel inspired, take a moment to reflect on the connections that exist all around you, both in nature and beyond. Imagine a world where volcanoes create their own lightning, a phenomenon born from electrified ash. When an explosive eruption occurs, a massive cloud of ash, dust, and gas surges high into the atmosphere. Inside this turbulent plume, countless particles collide, each impact transferring tiny amounts of electric charge. Lighter particles tend to gain a positive charge, while their heavier counterparts accumulate a negative charge. This separation of charges turns the entire plume into a chaotic electrical generator. As the difference between these charges grows, powerful electric fields emerge, resulting in stunning flashes of lightning within the volcanic cloud. These bursts of light illuminate the swirling ash column, unveiling intricate structures that would otherwise remain hidden in darkness. Volcanic lightning offers scientists valuable insights into the dynamics of eruptions. The electrical activity mirrors the vigor and turbulence of the plume, revealing a deeper understanding of these natural events. This phenomenon also highlights nature's ability to generate electricity in environments far removed from typical thunderstorms. It serves as a reminder that electrical forces arise wherever energetic particles collide in great numbers, transforming volcanic eruptions into some of the most electrifying spectacles on our planet. Take a moment to consider the vast sea of electric charge that surrounds us, a testament to the wonders of nature. Imagine standing outside on a perfectly calm day. The air around you feels serene, yet it carries a subtle, invisible energy, a collection of charged particles drifting like an unseen ocean. This background charge forms as sunlight interacts with molecules in the atmosphere, knocking electrons free and creating ions that wander in every direction. As you take a breath, you might not realize that dust, pollen, water droplets, and even tiny bits of organic material are constantly moving and redistributing these charges. The ground beneath you typically holds a net negative charge, while the air above carries a slight positive one. Together, they create a gentle vertical electrical gradient that stretches across the sky. This gradient intensifies near storms and softens in dry, still conditions, but it never entirely vanishes. Even indoors, traces of this atmospheric electricity linger in the air, influenced by airflow, humidity, and the materials around you. Although most people never directly sense it, this constant drift of charge subtly shapes cloud formation, affects particle movement, and even determines how easily you might accumulate static electricity. Think of the atmosphere as a vast electrical environment, alive with tiny movements of charge that persist day and night. It's a quiet reminder of the unseen forces that surround you, inviting you to explore the wonders of the world in which you live. Tiniest, if you feel inspired, take a moment to reflect on these hidden energies and how they connect you to the universe. Imagine a world where invisible electric fields connect every object you see. Each item carries some form of electric charge, even if it feels neutral to you. These charges give rise to electric fields that stretch outward, influencing how particles interact long before they come into contact. Though invisible, these fields play a crucial role in everyday phenomena, whether it's dust sticking to surfaces, hair standing on end due to static electricity, or molecules bonding with one another. The strength and direction of these electric fields depend on the types and arrangements of charges on objects. They can combine or repel each other in intricate ways. Electric fields guide electrons in circuits, play a role in the formation of lightning, and even affect how particles settle or disperse in the atmosphere. Even in the vastness of deep space, electric fields shape the movement of plasma around stars and planets. The entire physical world is structured by these unseen gradients, silently and consistently influencing every form of matter. What we often perceive as empty space is anything but. At incredibly small scales, the vacuum is alive with fluctuations of electric and magnetic fields, appearing and disappearing too swiftly for our senses or instruments to detect. This restless electrical nature of space reminds us that there's much more happening around us than meets the eye. As you reflect on this, consider how these unseen forces shape your everyday experiences. Wouldn't it be fascinating to delve deeper into the mysteries of the universe? Quantum theory reveals a fascinating world where restlessness reigns, characterized by a constant dance of virtual particles that flicker into existence and vanish almost immediately. These fleeting fluctuations exert subtle forces, influencing how objects interact, altering atomic behavior, and even changing the way light travels through space. In specific scenarios, like the space between two closely positioned metal plates, the vacuum reveals its unique character, behaving differently than it does in open environments. This behavior indicates that the vacuum possesses measurable electrical properties, suggesting that space is not merely a passive backdrop. Instead, it is a vibrant medium with its own intricate structure. Every beam of light, every charged particle, and each electromagnetic wave traverses this shimmering quantum landscape. The electrical nature of the vacuum quietly yet profoundly shapes our universe, showing that even what appears to be nothingness is alive with unseen motion. Consider the electric eel, a creature capable of sculpting its environment with powerful pulses of electricity. These eels generate remarkably strong electrical discharges through specialized organs formed from modified muscle cells, which function like biological batteries. These cells are arranged in long series, and when they all fire simultaneously, they create a potent electrical pulse. This pulse can stun prey or deter potential predators, illustrating the extraordinary power of nature's design. As you reflect on these concepts, you might find yourself intrigued by the hidden complexities of our universe. Would you like to continue exploring this captivating realm of science, or perhaps take a moment to rest? Imagine a world beneath the water's surface, where the eel is not just a creature of shock, but a master of subtlety. It emits gentle pulses, akin to an electrical form of echolocation, which helps it navigate through murky waters where vision is limited. These delicate signals allow the eel to sense objects and track moving animals, revealing its surroundings in a unique way. Recent studies uncover an intriguing aspect of the eel's hunting strategy. It can influence the behavior of its prey with rapid flickering pulses that cause muscles to contract involuntarily, effectively uncovering hiding spots. This dynamic use of electricity is essential for the eel, shaping its environment and bending the behavior of other creatures around it. In this realm, some fish communicate through invisible electrical fields. In areas where visibility is poor and sound is unpredictable, certain species rely on these weak electrical signals as their primary means of interaction. Equipped with specialized organs, these fish generate faint but steady electrical fields around themselves. When another fish approaches, it distorts this field, enabling both to sense each other without physical contact. Many of these species can adjust the frequency or pattern of their electrical emissions, sending messages that reveal their identity, sex, social status, or territorial boundaries. It's a fascinating dance of communication, hidden beneath the surface, where the language of electricity connects life in ways we are just beginning to understand. As you reflect on this intricate world, consider the remarkable strategies and connections that exist all around us, waiting to be discovered. Would you like to dive deeper into this underwater realm, or perhaps take a moment to ponder the wonders of nature? Imagine a world where signals are so precise that fish can easily tell their own kind apart from others in the same habitat. Some species even perform electrical duets, skillfully adjusting their frequencies to avoid interference. This elegant dance of communication enables them to maintain clear connections in environments where other senses may fall short. The underwater realm is alive with hidden electrical conversations, offering a unique perspective on how these creatures perceive and interact with their surroundings. Picture static electricity lifting tiny particles into floating clouds of dust. When surfaces rub against each other, electrons shift, creating areas of positive and negative charge. At a small scale, these charges can become powerful enough to move lightweight particles like dust, ash, or pollen. Under the right conditions, these particles can rise from the ground, seemingly defying gravity. In deserts, this phenomenon contributes to swirling dust storms, where grains are lifted by the winds and sustained by the electrostatic attraction between charged particles. Even on distant moons or asteroids with weak gravity, static charge can cause dust to levitate, drifting in shimmering halos above the surface. Isn't it fascinating to think about how these intricate interactions shape the lives of creatures in such diverse environments. As you reflect on this, consider the wonders of communication and connection that exist all around us. Would you like to continue exploring these mysteries, or perhaps take a moment to rest? Scientists suggest that certain patterns observed on lunar soil are influenced by a fascinating phenomenon. Even indoors, you might notice tiny specks clinging to screens, fabrics, or plastic objects. This occurs because static forces can overpower their weight, and while these effects may seem minor, they highlight the remarkable strength of electrical interactions in guiding the motion of particles that surround us. Interestingly, some minerals generate electricity simply through compression. Certain crystals and minerals exhibit a property known as piezoelectricity, which enables them to produce an electrical charge when they are squeezed, stretched, or bent. This happens because their internal atomic structures are arranged in a way that lacks perfect symmetry. When pressure is applied, the balance of charge within the crystal shifts, creating an electrical potential that can be detected on the surface. Quartz is one of the most well-known examples of this phenomenon, but many other minerals and engineered materials share this intriguing ability. This property serves as the foundation for a variety of technologies. For instance, small sensors can measure changes in pressure by transforming mechanical stress into electrical signals. Lighters utilize sudden compression to create sparks that ignite fuel. Even the tiny timekeeping crystal found in many watches relies on this effect to maintain a consistent vibration pattern. Isn't it fascinating how something as simple as pressure can lead to such complex and useful outcomes? You are invited to explore this world further, or perhaps take a moment to reflect on these connections. In the natural world, certain minerals known as piezoelectric materials can generate subtle electrical signals during events like earthquakes or landslides. This intriguing relationship between mechanical pressure and electrical energy reveals how interconnected these forces truly are. Crystals, for instance, possess the remarkable ability to convert motion into electrical charge. Beyond mere compression, some crystals can transform various types of mechanical motion into electrical energy. When they are twisted, tapped, or flexed, their internal structure adjusts, separating charge and producing a measurable voltage. This unique property has paved the way for innovative devices that harness energy from our everyday actions. Imagine floors embedded with piezoelectric materials that capture the pressure of footsteps, converting it into small amounts of electricity. Sensors placed on bridges or buildings can detect tiny vibrations, translating them into continuous signals that help monitor structural integrity. Even musical instruments can utilize these materials to convert sound vibrations into electrical output. At an atomic level, this phenomenon occurs when the arrangement of charged ions within the crystal is asymmetric. This allows forces to redistribute electrons whenever the crystal moves. Isn't it fascinating how nature can inspire such creativity and technology? As we explore these connections, consider how we might continue to harness the power of these extraordinary materials in our daily lives. Engineers are actively exploring new materials to enhance energy capture, aiming to create systems that harness ambient vibrations from sources like traffic, machinery, or ocean waves. This pursuit is grounded in a fundamental principle: motion can be transformed directly into electrical charge. The earth beneath your feet serves as a colossal electrical reservoir, containing a vast store of negative charge. This reservoir interacts continuously with the atmosphere above, creating a dynamic balance. Solar radiation, cosmic particles, and various weather processes constantly strip electrons from air molecules, allowing many of these electrons to eventually return to the ground, sustaining a long-term equilibrium. The Earth's surface acts as a stable reference point for electrical potential, anchoring the global circuit that flows between the ground and the upper atmosphere. When lightning strikes, it briefly reconnects regions of separated charge, sending immense energy back into the Earth. Moreover, the soil and rock play a crucial role in this electrical flow. Factors such as moisture content, mineral composition, and temperature significantly influence conductivity. Interestingly, some animals, including burrowing insects and subterranean mammals, may even detect electrical cues in the soil, using them as a part of their navigation. As you reflect on these intricate systems, consider the balance and connections that exist all around us. It invites you to think about the unseen energies that shape our world. If you're curious to learn more or wish to pause and absorb this information, feel free to continue or take a moment to rest. Imagine a vast planetary reservoir, functioning quietly yet profoundly, enabling countless electrical processes to unfold safely and continuously. This dynamic system supports both the wonders of nature and the intricacies of human technology. You may not realize it, but Earth is enveloped in a global electric circuit. From the surface to the upper atmosphere, a steady flow of electrical energy circulates, creating connections that are both essential and intricate. Thunderstorms, for instance, generate powerful upward currents that propel positive charges into the ionosphere, a region high above the clouds. Meanwhile, in areas of fair weather, a gentle downward flow allows charges to return from the ionosphere back to the ground. Together, these currents form a vast loop known as the global electric circuit. Even on the calmest of days, this system remains active, with subtle electric fields bridging the atmosphere and the surface. While lightning may capture your attention with its dramatic display, it is only a single aspect of this complex circuit. Countless small-scale discharges, turbulent air flows, and the movement of ions all contribute to the larger pattern. Researchers have found that variations in this global circuit can reflect shifts in climate, volcanic activity, or solar conditions, making it a vital indicator of planetary dynamics. This immense electrical loop surrounds you and every living being, weaving together the atmosphere and the ground into a unified system that operates continuously. Isn't it fascinating to consider how interconnected we are with the natural world? As you reflect on this, take a moment to appreciate the unseen forces that sustain life on our planet. The ionosphere resonates with electrical waves that traverse the globe. High above the Earth's surface, this charged layer interacts with ultraviolet light and energetic particles from space, dislodging electrons from atoms. It acts as a natural electrical conductor, allowing low-frequency waves to travel remarkable distances without losing strength. These electromagnetic waves can reflect off the ionosphere and the ground, bouncing across oceans and continents in patterns that evoke echoes in a vast atmospheric chamber. This unique characteristic facilitates long-distance radio communication, enabling signals to reach far beyond the horizon. The ionosphere is also sensitive to solar storms, which can temporarily alter its density, disrupting wave propagation and resulting in stunning yet unpredictable changes in global electrical behavior. Interestingly, some migratory animals might instinctively sense these fluctuations. The ionosphere is a dynamic electrical barrier enveloping our planet, constantly shifting and carrying waves that can circle the Earth repeatedly. Each day, the wind shapes our electrical environment as a steady stream of charged particles flows outward from the sun, enveloping the solar system in a river of plasma. Isn't it fascinating how interconnected everything is? When solar wind reaches Earth, it interacts with our planet's magnetic field and atmosphere, influencing the delicate balance of electricity. Strong gusts can compress the magnetosphere, changing the flow of charged particles along magnetic lines, and sometimes enhancing the beauty of auroras. Even in calmer moments, the solar wind carries electric charge that slowly builds up in the upper atmosphere. These subtle shifts can impact radio communications, satellite operations, and even the structure of the ionosphere itself. Occasionally, the solar wind brings with it magnetic structures that reconnect with Earth's magnetic field, introducing extra energy into our system. The entire planet responds to these interactions, from changes in atmospheric conductivity to electrical currents that loop around the polar regions. The solar wind serves as a reminder that Earth's electrical environment is never isolated. It is continuously influenced by the dynamic activity of the sun. Meanwhile, thunderstorms contribute their own energy, pumping massive currents into the upper atmosphere. Within a towering thunderstorm, countless collisions between ice, water droplets, and rising air currents create distinct regions of electrical charge. This fascinating process generates powerful electric fields that lead to the striking phenomenon of lightning. Take a moment to reflect on how interconnected these elements are, shaping our world in ways we might not always see. Would you like to continue exploring this captivating topic, or perhaps take a moment to rest? Not all the currents stay within the clouds. Some of them flow upward toward the ionosphere, contributing to the global electric circuit. This upward movement creates blue jets and other high-altitude discharges, forming stunning electrical structures that reach far into the sky. These currents play a crucial role in atmospheric conductivity, helping to maintain the delicate balance between the ground and the heavens. Thunderstorms act as natural generators, continuously replenishing the electric potential of the upper atmosphere. Without these storms, Earth's electrical environment would slowly fade away. Their influence goes beyond just weather. They also impact radio propagation, atmospheric chemistry, and the distribution of charged particles around the planet. Each storm serves as a dynamic engine, pumping electrical energy upward with remarkable intensity. The stability of matter is rooted in electrical attraction. Atoms hold their structure through a delicate interplay between negatively charged electrons and positively charged protons. Electrons don't orbit the nucleus like tiny planets. Rather, their electrical attraction binds them to specific energy levels, creating the stability we observe. Isn't it fascinating how interconnected everything is? Each element plays its part in the grand orchestra of our environment. Feel free to take a moment to reflect on this magnificent balance in nature. Imagine the world around you, shaped by the unseen dance of electrons. These tiny particles swirl around the nucleus of an atom, creating distinct patterns based on their motion and charge. Without this electrical force, matter would dissolve into a chaotic cloud of particles, lacking form and structure. The arrangement of these electrons is crucial. It determines how atoms bond and how molecules come together, influencing the very behavior of materials. Whether an object is brittle, flexible, metallic, transparent, or magnetic hinges on how these electrical forces guide the electrons. Even the colors you see are linked to these energy structures, as atoms absorb and emit specific wavelengths of light during electron transitions. In essence, the solidity you perceive in the world is a direct consequence of electrical attraction at the atomic level. It brings order to what would otherwise be chaos. Electricity is the vital force that enables matter to maintain its stable form. Each physical object remains intact due to the extraordinary strength of electrical forces binding its particles together. Protons and electrons attract each other, while electrons repel one another, and these interactions shape the very essence of all matter. When you place your hand against a solid surface, you never truly make contact at the atomic level. Instead, it is the electrical repulsion between the electrons in your hand and those in the surface that keeps these particles from overlapping. Take a moment to reflect on this intricate balance of forces that defines your reality. Isn't it fascinating how something so small can hold such power? You might find it comforting to know that this intricate dance of electrons ensures the stability of everything around you. If you feel inspired, continue exploring this fascinating realm, or take a moment to pause and appreciate the wonders of the universe. You may find it fascinating how the forces of electricity shape the very essence of matter around you. The sensation of solidity you experience stems from the repulsion of particles, a dance orchestrated by the arrangement of electrons. This interplay is crucial. It influences the behavior of metals, liquids, crystals, and gases. Even the intricate chemistry of reactions relies on the shifting electrical attractions between atoms, determining when bonds form or break. Imagine a world where electricity doesn't exist. In such a realm, atoms would struggle to maintain their boundaries, and molecules would fail to hold their shapes. Life, as we know it, could not emerge. The stability of everything, from towering mountains to the tiniest microorganisms, reflects the elegant balance of electrical forces at work. As you delve deeper, consider the movement of electrons. They defy our everyday understanding of reality. Rather than behaving like tiny balls on predictable paths, electrons follow the intriguing rules of quantum mechanics. In certain situations, they can act like waves, particles, or even something in between. Within atoms, electrons inhabit permitted regions of space, forming clouds of probability that hint at where they might be found. In various materials, electrons exhibit remarkable behaviors. They can flow freely, localize themselves, or create collective patterns that mimic entirely new types of particles. They can even traverse barriers that classical physics suggests should halt them, responding instantly to changes from afar and interfering with themselves in ways that challenge intuition. As you reflect on this intricate world, consider how these unseen forces shape your reality. Would you like to explore more about the mysteries of the universe, or perhaps take a moment to rest? You are stepping into a world where the behavior of electrons shapes the very foundation of modern electronics, chemistry, and biological processes. To truly grasp the nature of electrons, you need to set aside familiar notions of motion and position. Instead, you embrace a realm dominated by probability and wave-like behavior. Imagine electricity flowing effortlessly through supercooled materials, where resistance is non-existent. In typical conductors, electrons navigate through a material, frequently colliding with atoms, which transforms some electrical energy into heat. However, when certain materials are cooled to extremely low temperatures, something remarkable occurs. Electrical resistance drops to zero. In this superconducting state, electrons pair up in a harmonious dance, gliding through the material without scattering. Picture currents in a superconducting loop, flowing endlessly, losing no energy at all. This extraordinary property leads to the creation of powerful electromagnets, enables efficient power transmission, and allows for the development of highly sensitive scientific instruments. Furthermore, the transition to superconductivity changes how materials interact with magnetic fields, causing them to expel these fields and creating stunning phenomena, such as magnets that seem to float. While scientists tirelessly search for materials that can achieve this state at higher temperatures, the discovery of superconductivity stands as one of the most astonishing revelations in the field of physics. As you explore this fascinating topic, consider how these principles might influence the future of technology and our understanding of the universe. Would you like to continue this journey into the wonders of science, or perhaps take a moment to reflect on what you've learned? As you explore the fascinating world of superconductors, you discover that the electrical behavior of materials can change dramatically when they approach their quantum limits. Imagine a superconductor that not only carries current without resistance, but also repels magnetic fields from its interior. This remarkable phenomenon, known as magnetic flux exclusion, allows a magnet placed near a superconductor to float in a stable position, either above or beside it. Picture this: the superconductor generates circulating currents on its surface that counteract the magnet's field, holding it in place without any physical contact. This levitation is impressively stable, resisting any tilting, sliding, or rotation. Engineers envision harnessing this effect for frictionless transportation, precision bearings, or ultra-stable platforms for scientific instruments. This phenomenon reveals the astonishing power of coordinated electron behavior, the currents that enable levitation flow without energy loss, creating a scene that feels almost magical, where magnets hover effortlessly. It's a striking showcase of how quantum electrical effects can manifest in ways we can observe and appreciate on a human scale. Moreover, some materials possess the intriguing ability to remember past electric fields in mysterious ways. What other secrets might they hold? As you ponder this, consider the endless possibilities that lie ahead in the realm of superconductivity. Certain substances possess a fascinating property known as ferroelectricity. This allows their internal electric polarization to change direction when influenced by an external field, and intriguingly, they can maintain this new state even after the field is removed. It's almost as if these materials have a memory of previous electrical conditions. Within these substances, small regions called domains align their dipoles in specific orientations. This alignment creates stable patterns that can encode information. Remarkably, these patterns can last for extended periods, making ferroelectric materials invaluable for applications such as memory storage, sensors, and precise control devices. The process of switching involves tiny shifts in atomic positions, which collectively lead to microscopic changes in electrical properties. Factors like temperature, pressure, or mechanical stress can significantly affect how these domains form and reorganize over time. Researchers are drawn to the study of ferroelectricity, not only for its practical uses, but also because it unveils profound connections between electrical behavior and atomic structure. The ability of a material to retain an imprint of past electric fields illustrates the intricate and surprising ways electricity interacts with matter. Isn't it captivating how electricity can travel through certain materials as waves of vibration? This exploration opens up a world of possibilities in understanding our universe. If you're intrigued, consider delving deeper into this subject, or perhaps take a moment to reflect on the wonders around you. Imagine a world where the very nature of energy is transformed. In certain solid materials, electrical interactions intertwine seamlessly with mechanical vibrations, giving rise to a unique phenomenon known as phonon polaritons. These fascinating waves enable energy to traverse through a material not just as moving charges, but also as oscillations within the atomic lattice. This remarkable coupling opens up exciting new avenues for controlling heat, light, and electrical flow on a microscopic scale. Materials that can harness these waves possess the ability to confine energy into spaces far smaller than the wavelength of light. This capability paves the way for the development of miniature sensors and advanced optical devices. Moreover, the wave-like nature of these interactions affects how materials emit or absorb infrared radiation, making them crucial for thermal imaging and energy harvesting technologies. In the natural world, similar coupling effects play a vital role in regulating how heat distributes itself through minerals and biological tissues. Consider how the concept of electricity moving as a vibration rather than merely as a flow of electrons deepens our understanding of energy transmission in condensed matter. Quantum tunneling further enhances this narrative, allowing electric charges to slip through barriers that classical physics would deem insurmountable. In this quantum realm, particles like electrons can sometimes appear on the opposite side of a barrier, defying conventional expectations. This intriguing process occurs because electrons exhibit wave-like properties, allowing them to extend into regions that traditional physics would restrict. As you reflect on these concepts, you may feel a sense of wonder about the complexities of energy and matter. The journey of understanding continues, inviting you to explore further or pause to contemplate these remarkable ideas. Imagine a barrier so thin that part of a wave can slip right through it. This phenomenon, known as tunneling, allows an electron to emerge as if it has passed directly through the barrier. Tunneling is more than just a curious aspect of quantum mechanics. It plays a vital role in many technologies we rely on today. For instance, scanning microscopes utilize tunneling currents to create detailed maps of surfaces, while various components in advanced circuits depend on this effect to regulate electron flow. Tunneling also has profound implications for natural processes, especially within stars. It enables nuclear fusion, allowing charged particles to overcome their natural electrical repulsion. In the realm of biology, certain reactions hinge on tunneling to facilitate the movement of protons or electrons between molecules. This remarkable phenomenon illustrates how quantum mechanics influences both the tiniest details of our technology and the vastness of the universe. Now consider electron spin. This intrinsic property of electrons generates tiny magnetic fields that impact all technology. Each electron possesses an angular momentum known as spin, which results in a magnetic moment even when it is stationary. This subtle magnetic characteristic affects how atoms bond and how materials display magnetism. In ferromagnetic materials, the spins of numerous electrons align, producing robust magnetic fields that power motors, data storage devices, and countless tools. Furthermore, electron spin is central to cutting-edge technologies like spintronics. This innovative field leverages spin states rather than merely charge flow to store and process information. As you reflect on these concepts, you may find yourself marveling at the interconnectedness of quantum mechanics, technology, and the natural world. If you wish to explore these ideas further, take a moment to pause and consider the fascinating ways in which they shape our understanding of reality. Imagine a world where spin-based devices not only promise faster performance, but also consume less energy. At a deeper level, the alignment and interaction of electron spins shape the magnetic structures of planets, the behavior of stellar remnants, and the intriguing properties of exotic materials like quantum magnets. The very existence of electron spin creates a universe influenced by magnetic interactions that are both familiar and extraordinary. Picture electrons moving in a perfectly coordinated dance. When they traverse certain materials, They don't just collide randomly with atoms. Instead, under the right conditions, their movements synchronize, forming collective waves that glide with remarkable grace and precision. This organized flow emerges in materials where electrons strongly interact, creating patterns akin to a synchronized performance across a vast ensemble. Such behavior can significantly impact electrical resistance, heat transport, and even the optical properties of materials. In metals close to absolute zero, electrons can adopt unexpectedly smooth flow patterns, resembling fluid movement. In some exotic materials, they arrange into repeating structures that intricately alter conductivity in fascinating ways. Isn't it captivating to think about how these microscopic dances shape the world around you? As you reflect on this, consider the remarkable implications of these interactions. You might find yourself wondering how this knowledge could influence future technologies or deepen your understanding of the universe itself. If you wish to explore more about these intriguing phenomena or take a moment to reflect, you're welcome to continue or pause as you see fit. You find yourself captivated by the ongoing discoveries in the world of science, particularly those surrounding the intricate dances of particles. Imagine swirling patterns that shape magnetic behavior and oscillations that influence superconductivity. The exploration of these flowing electron states reveals a fascinating truth. Electricity moves with a grace that goes far beyond mere current. In this collective system, countless particles merge into a unified motion, showcasing a remarkable harmony. Metals, for instance, carry electricity because their electrons have the freedom to roam almost unrestrained. Within a metal, many electrons are not bound to individual atoms. Instead, they drift through the material in a shared space that weaves throughout the entire structure. This remarkable freedom arises from the arrangement of metal atoms in a repeating lattice. This organization allows their outer electrons to overlap, forming a communal sea of charge. When an electric field is applied, these free electrons respond almost instantaneously, shifting through the lattice and generating the current that powers our devices and illuminates our surroundings. The efficiency of this movement is influenced by various factors, including temperature, crystal structure, and the presence of impurities within the metal. As the material cools, the atomic lattice vibrates less, enabling electrons to flow more smoothly. This is why some metals become far better conductors at lower temperatures. As you reflect on these discoveries, you may wonder about the beauty and complexity of the natural world around you. It's a reminder that there is always more to learn and explore. Feel free to continue your journey of discovery, or take a moment to rest and absorb this knowledge. Metals shine with a brilliance that captures your attention, thanks to the free movement of electrons. When light strikes a metal's surface, it interacts with these electrons, reflecting outward and creating that distinctive luster. This unique combination of optical and electrical properties makes metals invaluable, not only in the realm of modern technology, but also in ancient craftsmanship. On the other hand, insulators play a crucial role in our safety. They keep their electrons closely bound to their atoms, making it challenging for electrical charges to flow through them. This stability is a result of strong chemical bonds that effectively lock the electrons in place, preventing the formation of free carriers that could generate a current. Materials like rubber, glass, and certain plastics utilize this characteristic to shield both people and equipment from unwanted electrical currents. When voltage is applied to an insulator, the electrons resist movement, ensuring safety and maintaining a clear separation between conductive components. The insulating properties of these materials depend on various factors, including their molecular structure internal defects, and environmental conditions, such as humidity. Interestingly, in nature, many organisms rely on insulating layers to protect their sensitive tissues from electrical fluctuations in their surroundings. Even the atmosphere functions as a partial insulator, only allowing electrical fields to grow strong enough to create phenomena like lightning. Isn't it fascinating how both metals and insulators work in tandem, shaping our technological landscape and natural world? As you reflect on this interplay, consider how these materials influence your daily life and the safety measures that protect you. Insulators play a crucial role in containing electrons, making them essential for managing the strong forces generated by electricity. Semiconductors act as controlled gateways for electrical flow, sitting at an intriguing midpoint between conductors and insulators. Here, electrons are not entirely free. However, they can be set in motion with the right stimuli, such as light, heat, or applied voltage. This unique behavior stems from the carefully arranged atomic structure within semiconductors and the energy bands that govern electron movement. By introducing small amounts of other elements into the material, engineers can fine-tune the ease with which electrons or holes travel, creating specific regions with distinct electrical properties. These specialized areas work together to form essential components like diodes and transistors, which are fundamental to modern electronics. The precision with which we can control electron flow enables semiconductors to amplify signals, switch currents, and process information. Their functionality adapts to changes in temperature and light, making them perfect for applications in sensors and photovoltaic devices. In essence, semiconductors lay the groundwork for computing, communication, and energy technologies, transforming the controlled movement of electrons into a vibrant digital landscape. As you explore this fascinating world, consider how these tiny components influence our daily lives. Would you like to delve deeper into any specific aspect of semiconductors? Feel free to continue your journey or take a moment to reflect on the marvels of technology. Transistors are remarkable devices that make tiny electrical decisions, creating entire worlds of logic. They operate by either allowing or blocking the flow of electrons based on a small input signal. This seemingly simple action becomes incredibly powerful when billions of transistors are combined into circuits, enabling them to perform complex logical operations. Each transistor functions like a switch, controlling the flow of current along specific pathways. This coordination allows computing systems to carry out mathematical processes, store data, and execute intricate instructions. When these switches work together, they can represent information, compare values, or direct signals along various routes. The speed at which transistors change state is crucial, as it determines how quickly a computer can function. Engineers are constantly refining their designs to enhance energy efficiency and performance. Despite their tiny size, the collective behavior of transistors forms the foundation of our modern digital lives. From navigation systems to medical devices, countless technologies rely on the electrical decisions made at this microscopic scale. The transistor is truly one of humanity's most transformative inventions, translating the movement of electrons into logic, communication, and creativity. As you reflect on the impact of transistors, consider how they shape the world around you, connecting you to a vast network of information and possibilities. Would you like to explore more about how these tiny components influence your daily life? Imagine a world where information is stored as patterns of electric charge. This is the foundation of computer memory. Various types of memory utilize the presence or absence of charge to represent data. In some systems, tiny capacitors hold small amounts of electrical energy, signaling whether a bit is in one state or another. Other technologies trap electrons within insulating layers, enabling data to remain intact even when the power is off. The stability of these stored charges hinges on the materials used, temperature, and precise engineering. To read this information, we detect tiny variations in voltage or current. Writing data involves rearranging the distribution of electrons within microscopic cells. As technology progresses, memory components shrink to astonishingly small sizes, allowing immense amounts of information to fit into compact devices. This reliance on electric charge reveals that even the most abstract digital concepts are grounded in physical processes. Every photograph, message, or program in modern computing exists because electrons can be arranged into stable, retrievable patterns. Consider this: every digital image you encounter is created by streams of electrical signals. Before a picture graces your screen, it starts as a complex flow of electrical information, navigating through circuits, processes, and memory. Imagine each pixel on your screen as a tiny puzzle piece, each one defined by specific electrical values that determine its color and brightness. These signals journey along intricate pathways crafted by transistors, amplifiers, and timing systems, working together to synchronize the movement of electrons with extraordinary precision. In cameras, light is transformed into electrical charge by sensors that react to incoming photons. This charge is then interpreted and stored as patterns that accurately represent the scene before you. When it's time to display the image, the electrical instructions for each pixel travel to the screen, guiding minuscule elements to create the correct colors. This rapid coordination of millions of electrical signals enables images to update seamlessly, allowing for smooth videos and interactive displays. While digital pictures may appear effortless, they depend on a constant flow of electricity, navigating through meticulously designed systems that convert information into a visible format. Electricity also empowers lasers to generate perfectly ordered light. A laser produces an exceptionally pure beam by stimulating atoms or molecules, causing them to emit photons that align in direction, frequency, and phase. This process is fueled by electricity, which provides the energy needed to elevate these atoms into higher energy states. As you reflect on this intricate dance of technology, consider the remarkable systems at work, transforming light and electricity into the vivid images you experience every day. If you're curious to learn more about how this technology shapes our world, feel free to continue exploring or take a moment to rest. Imagine a world where light is not just a natural phenomenon, but a powerful tool. When a photon is released by one atom, it sparks a chain reaction. Neighboring atoms respond in kind, emitting identical photons in a process called stimulated emission. This creates a focused beam of light that travels vast distances with minimal spreading. Engineers harness electrical control to refine the properties of lasers. They can adjust brightness, color, and pulse duration, enabling a wide array of applications. From precision cutting of metals to reading data from storage devices, lasers are integral to both scientific research and medical technology. Their incredible abilities stem from the electrical energy that initiates this process, underscoring the vital role electricity plays in crafting one of our most precise instruments. Now consider plasma displays. These fascinating screens utilize electrified gas to bring images to life. Each pixel houses a tiny cell filled with gas that becomes ionized when an electrical voltage is applied. This ionized gas emits ultraviolet light, which then interacts with a phosphor coating inside the cell. The phosphor transforms this invisible light into vibrant, visible colors. By carefully controlling the electrical pulses sent to each cell, the display can create a stunning array of hues and brightness levels. Isn't it remarkable how electricity shapes the technology around us? Imagine the fascinating world of plasma cells, where rapid movements create smooth transitions and striking contrasts. While newer technologies have gained popularity, plasma displays continue to serve as a remarkable example of how electricity can illuminate our surroundings through ionized gas. Each pixel, with its glowing plasma, acts like a tiny lamp, brightening and dimming with precise electrical control. This intricate dance of electrified matter reveals how complex images can arise from microscopic interactions. Now consider the role of electric motors. These remarkable devices transform invisible forces into tangible motion. And electric motors are the driving force behind countless devices, from fans and household appliances to industrial machinery and transportation systems. Their remarkable ability to convert invisible electrical energy into motion makes them one of the most vital technologies in our modern world. This transformation illustrates just how profoundly electricity influences our physical environment. Consider the human body. It generates continuous movement through everyday actions like walking, stretching, and shifting posture. This natural motion can be harnessed to produce wearable electrical energy. Flexible materials are designed to capture mechanical motion at these small scales, converting pressure or bending into electrical charge. Some materials generate electricity when stretched, while others do so through repeated compression. When these materials are integrated into wearable devices, they can harvest energy from routine activities without requiring any conscious effort from you. The electricity generated can power sensors that track movement, measure environmental conditions, or monitor health indicators. The effectiveness of these systems hinges on the flexibility and durability of the materials, as well as their ability to collect charge while allowing for free movement. Engineers are exploring a range of structures, including woven films, layered polymers, and tiny embedded generators that respond to motion at specific points on the body. As you reflect on these advancements, consider how they might enhance your daily life. The potential is vast, and the journey of innovation continues to unfold. Would you like to explore these possibilities further, or perhaps take a moment to appreciate the current state of technology? Imagine a world where your everyday movements generate energy. This innovative approach harnesses the natural activities you already engage in, transforming your body into a quiet powerhouse for small-scale energy systems. The human body is not just a vessel for movement, it can also contribute to sustainable energy sources. Picture electric textiles that might one day power your clothing through your own body movements. Recent advancements in material science have made this vision a reality. Conductive fibers, flexible circuits, and energy-generating structures can now be seamlessly integrated into fabrics. These textiles respond to bending, stretching, or rubbing, producing small yet measurable electrical signals. Unlike traditional, rigid devices, these fabrics move with you, ensuring comfort while introducing new functionalities into your daily attire. Imagine patterns of conductive threads woven throughout the material, allowing energy to be collected and stored for later use. The choice of fiber, weave, and coating plays a crucial role in how effectively these materials respond to your movements. Some designs even feature conductive pathways combined with micro-storage elements. This means that the fabric can generate and hold energy simultaneously. The the potential applications are vast. Think about health monitoring systems, navigation aids, and emergency signaling tools that could operate independently without the need for external power sources. As you reflect on these possibilities, consider how close we are to integrating energy-generating textiles into our lives. The future of clothing might just be a step away. Would you like to continue exploring this fascinating topic, or perhaps take a moment to rest? Imagine a future where clothing transforms from a simple layer of protection into an active energy harvesting surface that responds to your every movement. This innovative concept of electric textiles opens up exciting possibilities. Wireless charging is at the heart of this evolution. It enables energy to flow through invisible power fields, allowing electrical energy to be transferred without any physical contact. This is achieved by creating an oscillating magnetic field, which induces current in nearby devices. The process relies on two specially tuned coils, positioned close together to facilitate efficient energy transfer. The transmitting coil generates a dynamic magnetic environment, while the receiving coil guides electrons into motion. The success of this method hinges on several factors, including coil alignment, distance, and the materials surrounding the system. Engineers are continually refining coil geometry and frequency to enhance power transfer and minimize energy loss. Thanks to wireless charging, devices can recharge without the hassle of exposed connectors or direct wiring, making life more convenient and reducing wear on components. This technique can also be expanded to larger systems. Imagine embedded coils in floors, vehicles, or furniture, seamlessly providing power to compatible devices. This approach illustrates the potential of magnetic fields to serve as intermediaries in the transfer of electrical energy, paving the way for new connections and interactions between devices. As you consider these advancements, how do you envision the future of your everyday interactions with technology? Would you embrace such innovations in your clothing? Induction cooking is a fascinating technology that heats metal without the use of flames. Imagine a cooking surface that relies on alternating magnetic fields to generate heat directly within compatible cookware. As the magnetic field interacts with the metal, it induces circulating currents, which encounter resistance. This internal resistance generates heat, warming your pot or pan while leaving the surrounding air and cooking surface cooler. One of the standout features of induction cooking is its ability to provide rapid temperature changes. Energy is delivered straight into the cookware, bypassing any intermediate heating elements. The efficiency of this method hinges on several factors, including the magnetic properties of the metal, the thickness of the cookware, and the strength of the magnetic field. You'll appreciate the precise control induction cooking offers, as it reduces energy waste by concentrating heat exactly where it's needed. Additionally, it enhances safety. The cooking surface cools quickly once you remove the cookware. This innovative method beautifully illustrates the connection between magnetic fields and electrical currents, showcasing how electromagnetic principles can transform everyday tools. Just as magnetic levitation trains glide effortlessly using electrically controlled forces, induction cooking brings a new level of efficiency and safety to your kitchen. Wouldn't you like to explore more about how such technologies shape our daily lives? Imagine a world where transportation systems utilize the incredible power of electromagnetic interactions to seamlessly lift and propel vehicles. In this innovative design, there's no physical contact between wheels and tracks. Instead, controlled magnetic fields are generated by coils situated both within the train and along the guideway. As currents flow through these coils, they create forces that counteract gravity, allowing the vehicle to glide forward effortlessly. This absence of friction between surfaces means that trains can move smoothly, experiencing minimal mechanical wear. Engineers play a crucial role in this process, carefully monitoring field strength, alignment, and timing to ensure the train remains stable and centered on the track. The precision required is remarkable, yet the outcome is a mode of travel that marries speed with near-silent operation. The ability to lift and guide substantial structures using only electromagnetic forces showcases the extraordinary potential of coordinated electrical control. It illustrates how the principles of magnetism can transition from laboratory settings to practical transportation systems, enabling the movement of passengers across vast distances. Electric vehicles further exemplify this innovation. They convert stored charge from battery systems into motion, utilizing electric motors to propel themselves silently. This advanced technology not only enhances our travel experience, but also highlights the future of transportation, where efficiency and quiet operation reign supreme. As we explore these advancements, consider how they might shape the way we travel. Wouldn't it be fascinating to continue this journey together? As current flows through the coils of the motor, magnetic forces emerge, turning the rotor and propelling the wheels forward. Without combustion, this system operates quietly and generates fewer mechanical vibrations. The performance of an electric vehicle hinges on several factors: battery chemistry, motor design, power management systems, and the efficiency with which energy is recaptured during braking. Engineers are constantly striving to enhance how quickly energy can be stored, how far a vehicle can travel on a single charge, and how effectively heat is managed during operation. This focus on innovation ensures that the driving experience remains smooth as the motor delivers consistent torque across a wide range of speeds. Electric vehicles exemplify how advancements in electrical storage and motor technology can transform transportation. They reduce our reliance on combustion and showcase the adaptability of electrically driven motion. Batteries play a crucial role in this process, storing energy through reversible chemical reactions. They hold energy by arranging materials in such a way that controlled chemical reactions release electrons. When a battery powers a device, the internal chemistry shifts, allowing electrons to flow through an external circuit before returning to the opposite side of the cell. This intricate dance of energy is at the heart of electric mobility, inviting us to explore a future where transportation is not only efficient, but also harmonious with our environment. Would you like to dive deeper into this fascinating world, or perhaps take a moment to reflect on what you've learned? As you consider the fascinating world of batteries, you begin to understand how they work. When charging, the current you apply reverses chemical changes, restoring the original arrangement of materials within. The type of materials inside a battery plays a crucial role in determining its energy storage capacity, the speed at which it can release energy, and the number of cycles it can complete. Engineers are constantly experimenting with new combinations of metals, electrolytes, and separators to enhance both performance and durability. Factors such as temperature, discharge rate, and chemical stability significantly affect how effectively a battery operates. This intricate relationship between chemistry and electricity enables portable devices, vehicles, and backup systems to function without being directly connected to a power grid. Picture the battery as a bridge connecting chemical energy to electrical output, allowing countless technologies to operate independently. Among these innovations are flow batteries, which hold electrical energy in liquid form. These systems utilize liquid electrolytes that circulate through external tanks and across a central cell, where electrochemical reactions take place. Unlike traditional solid-state batteries, the energy capacity of a flow battery primarily depends on the size of the storage tanks rather than the internal cell itself. During discharge, the flowing liquids release electrons that travel through an external circuit, powering your devices. As you reflect on this technology, you might find yourself wondering how these advancements will shape the future. Feel free to continue exploring or take a moment to rest. When charging takes place, the process reverses, restoring the chemical composition of the electrolytes. This clever design contributes to a long cycle life, as the reactive materials stay in solution and endure less structural stress. By simply expanding the tanks, operators can enhance storage capacity, making flow batteries especially appealing for large-scale energy storage, such as stabilizing electrical grids. The efficiency of this system hinges on several factors: pump performance, membrane selectivity, and the chemical properties of the electrolytes. Flow-based storage presents a flexible approach to managing substantial amounts of electrical energy, utilizing circulating liquids instead of solid materials. On the other hand, ultracapacitors deliver electricity in rapid bursts. They store electrical energy by accumulating charge along the surfaces of specially designed electrodes, which are separated by a thin insulating layer. When energy is required, this stored charge can be released almost instantly, as it doesn't depend on slow chemical reactions. This rapid discharge makes ultracapacitors ideal for applications that demand sudden bursts of power, such as stabilizing voltage, supporting quick acceleration, or maintaining performance during brief interruptions in supply. Consider how these technologies might shape the future of energy storage and management. Would you like to explore more about their potential applications? Imagine a world where energy is harnessed with remarkable speed and efficiency. Ultracapacitors are at the forefront of this innovation, designed to charge rapidly and excel in repeated cycling. Their ability to store energy hinges on several factors, including the surface area of the electrodes, the composition of the electrolyte, and the distance between the charged layers. While they may not hold as much energy as batteries of a similar size, their quick response and durability make them valuable companions to other storage technologies. Consider how ultracapacitors demonstrate the management of electrical energy through physical charge separation rather than relying on chemical changes. This leads to systems that are finely tuned for rapid response. Now think about lightning rods. These fascinating devices safely guide electrical storms into the ground. By providing a controlled pathway for electrical discharge during a storm, a lightning rod serves as an elevated point that attracts the developing lightning strike. It connects to a low-resistance conductor, which channels the charge safely into the ground, preventing it from traveling through buildings or other structures. The effectiveness of this system relies on precise placement, grounding depth, and the conductivity of the surrounding soil. As a storm approaches and electric fields strengthen, the lightning rod becomes the preferred channel for that impending discharge. As you reflect on these technologies, consider how they shape our understanding of energy management and safety. Would you like to delve deeper into these concepts, or perhaps take a moment to rest? Imagine a current flowing seamlessly through a conductor, dispersing safely into the earth. This approach not only protects structures, but also minimizes fire hazards by guiding electrical events along a predictable path. Lightning protection systems illustrate how our understanding of natural electrical behavior can shield us from harm, allowing us to manage powerful atmospheric forces with simple, thoughtfully designed components. Generators play a vital role in this process, transforming motion into streams of electrons. Picture a shaft turning within a magnetic field. This simple action can generate electrical current. As the internal parts rotate, they alter the magnetic landscape inside the device. The surrounding electrons respond, moving along an organized path. The efficiency of this movement relies on the arrangement of coils, the strength of the magnetic field, and the consistency of the rotation. Various forces, be it water pressure, moving air, expanding vapor, or mechanical engines, can initiate the motion that keeps the system in motion. Within the generator, nothing is created or destroyed. Instead, existing electrons are encouraged to flow in a coordinated stream, resulting in usable electrical power. This conversion from mechanical motion to electrical flow underpins nearly every major energy network around the globe. As you reflect on these concepts, consider how interconnected our world is through the invisible currents that power our lives. Would you like to explore more about how these systems work? Imagine a world where electrons dance in harmony with a shifting magnetic field, creating a reliable current from something as simple as a rotating coil. This fascinating process reveals how mechanical forces can lay the groundwork for electrical systems that span vast distances. Picture turbines harnessing the energy of nature's movements, transforming the kinetic energy of flowing fluids into powerful electrical currents. As water or air moves, it's guided along specially designed blades within the turbine. The fluid's momentum causes these blades to rotate, turning a central shaft. This rotation then powers a generator, converting mechanical motion into a steady stream of electricity. The efficiency of the entire system hinges on the precise geometry of the blades, the consistency of the fluid flow, and the alignment of all components involved. Consider the steam rising in a power plant, the water cascading down a channel, or the air sweeping across open land. Each of these elements can ignite the turbine's motion. Engineers meticulously assess factors like turbulence, blade angle, and structural stability to ensure smooth, predictable motion. This intricate arrangement connects the natural movements of our planet directly to the production of electricity, transforming existing energy flows into a stable and renewable source of power. Isn't it remarkable how nature's forces can be harnessed to create something so vital? As you reflect on this, allow yourself to appreciate the seamless blend of design and nature that powers our world. If you feel inspired, take a moment to continue exploring or simply rest in this thought. Imagine a world where fluid motion plays a pivotal role in generating electricity. Hydroelectric dams harness the power of falling water, converting it into a reliable and potent energy source. Water stored in reservoirs holds potential energy simply because it is positioned above a lower elevation. When this water is released, it rushes through narrow pathways, gaining speed as gravity pulls it downward. This dynamic movement strikes the blades of a large turbine, setting it in steady rotation, which in turn drives a generator. The beauty of this system lies in its connection to the natural water cycle. Rainfall, snowmelt, and seasonal changes continuously refill the reservoirs, allowing the system to operate seamlessly. Engineers diligently monitor various factors, such as water pressure and flow rate, to ensure everything runs smoothly. The energy harvested from the descending water is influenced by the height difference, the design of the channels, and the turbine's efficiency. Because this process does not involve combustion, it stands as a clean and sustainable power source. Hydroelectric systems exemplify how the simple force of gravity can be transformed into electrical energy, supporting cities, industries, and remote communities alike. As you reflect on this, consider the remarkable ways nature and technology intertwine to create a brighter future. Would you like to delve deeper into this topic, or perhaps take a moment to rest? Wind farms harness invisible air currents to generate electric power. As the air moves, it carries kinetic energy, which is captured by aerodynamic blades that shape the airflow into rotation. As air flows past each blade, pressure differences create lift, causing the rotor to turn. This rotational motion travels down a shaft to a generator, where magnetic fields guide electrons, creating an organized electrical current. The efficiency of power extraction relies on several factors, including blade length, air density, atmospheric conditions, and the arrangement of the turbines across the landscape. Taller towers can access steadier air currents, while offshore installations benefit from the smoother airflow over open water. The rotation of the blades is gentle yet persistent, enabling the system to generate significant amounts of electricity over extended periods. What makes this method truly remarkable is its connection between atmospheric motion, which flows freely across our planet, and the electrical networks that power our modern lives. Ingeniously designed blades convert these invisible air currents into a reliable and renewable source of electricity. In contrast, solar cells utilize light to free electrons directly. The sunlight that reaches us carries energy in the form of photons, and photovoltaic devices harness this energy to liberate electrons within a semiconductor. Isn't it fascinating how these technologies transform natural forces into the electricity that fuels our daily activities? When photons hit a material, they can energize electrons enough to dislodge them from their usual positions. The internal structure of the device creates an electric field that directs these freed electrons along specific pathways, generating a direct current. The efficiency of this process relies on how well the material absorbs light, how easily the electrons move after being excited, and how effectively the device separates charges. By using different semiconductor compositions, engineers can adjust the device's response to various wavelengths of light. Layers of conductive metals, transparent coatings, and protective films all play essential roles in the overall functionality. The outcome is a technology that transforms sunlight into electrical energy without any moving parts. It beautifully illustrates how light can act as a direct source of charge motion when paired with precisely engineered materials. In a different approach, geothermal plants harness the Earth's heat to produce electricity. The heat rising from beneath the surface can be used to boil water or heat specialized fluids, creating vapor that expands with significant force. This expanding vapor travels through turbines designed to capture the rotational energy from the flow. Isn't it fascinating how various natural elements can be transformed into energy? As we explore these technologies, we might find new ways to harness the power around us. Feel free to take a moment to reflect on this connection between nature and innovation. Imagine a world where the Earth's heat transforms into energy. This process begins when rotation enters a generator, prompting electrons to move in response to shifting magnetic fields. In particular regions, geological formations rich in porous rock and naturally heated underground reservoirs make this transformation possible. Engineers drill into these formations to harness thermal energy, circulating fluid through them. The reliability of geothermal systems lies in the steady heat that emerges from deep within the Earth. Because the temperature difference remains consistent, these plants can operate with remarkable continuity. It's fascinating how heat that has been stored within the planet for ages can now support our modern energy systems. Now, consider tidal energy, which draws power from the moon's rhythms. As ocean water rises and falls in predictable cycles, Driven by the gravitational pull between Earth and its lunar companion, this movement creates kinetic energy. This energy is harvested when flowing water passes through underwater turbines or channels specifically designed to accelerate the current. As the water flows, it turns blades connected to a generator, converting that natural rhythm into electricity. The reliability of tidal energy stems from the stability of the orbital relationship that governs the tides. It's a remarkable reminder of how nature's patterns can provide us with sustainable energy solutions. Perhaps you feel inspired to explore further or reflect on the wonders of our planet's energy systems. Coastal areas with narrow inlets or strong tidal currents serve as ideal sites for energy extraction. Tidal systems need to be carefully designed to endure the challenges posed by corrosive saltwater, shifting sediments, and powerful waves. When engineered effectively, these systems provide a clean and highly reliable source of electrical energy. This method of energy generation connects the movements of celestial bodies, the dynamics of the ocean, and the production of electricity, illustrating the moon's ongoing impact on both life and technology. Interestingly, some microorganisms generate electricity as part of their metabolic processes. Certain microbes have developed the remarkable ability to transfer electrons outside their cells while breaking down nutrients. This unique trait enables them to interact directly with minerals or other surfaces in their surroundings. As these electrons flow outward, they produce detectable electrical currents that scientists can study. These microorganisms thrive in a variety of environments, such as riverbeds, wetlands, and nutrient-rich soils. Their metabolic pathways depend on specialized proteins that help transport electrons across cell membranes and onto external structures. The strength of the electrical current they generate is influenced by factors like nutrient availability, temperature, and the composition of their environment. As you reflect on these fascinating interactions in nature, consider how they connect to the broader themes of energy and life itself. If you wish to explore more about this intriguing subject, or take a moment to pause, feel free to do so. Researchers are currently delving into the fascinating ways we can utilize natural electrical processes for various applications, such as sensors, environmental cleanup, and tiny energy sources. The existence of these organisms reveals an astonishing link between life and the flow of electrical charge, showcasing that biological systems can generate electrical currents without any machinery. Imagine bacteria forming living wires that conduct electricity. Some of these bacterial communities create long filament-like structures capable of transporting electrons over significant distances, especially considering their small size. These remarkable structures enable entire colonies to share resources and coordinate metabolic reactions that rely on the transfer of electrons from external sources. These filaments act as conductive pathways, efficiently carrying charge from one point to another, particularly in environments where oxygen or other electron acceptors are unevenly distributed. The ability to create these biological wires is influenced by genetic factors, environmental conditions, and the presence of minerals that assist in electron movement. Scientists are investigating these systems to gain insights into how microbes organize themselves and how electrons traverse the filaments. The discovery of these living conductive structures not only captures our imagination, but also opens exciting new possibilities for bioengineered materials and devices. As you reflect on this, consider the potential this research holds for our future. Would you like to continue exploring this captivating topic, or perhaps take a moment to pause and absorb this information? The natural world has its own remarkable strategies for generating electrical charge, even in environments far removed from traditional electrical systems. Imagine scientists harnessing the power of microbes to create biobatteries. These biological systems, capable of generating or transferring electrons, can be assembled into devices that produce small but consistent electrical currents. These innovative devices rely on communities of microbes arranged thoughtfully. Their metabolic processes feed electrons into an external circuit, creating a continuous flow of energy. The materials housing these microbes are crucial. They must allow nutrients to enter, waste to exit, and electrons to move freely toward the electrodes. You might wonder how various factors influence these systems. The electrical output is affected by temperature, nutrient concentration, and the specific arrangement of microbial layers. While the energy generated may be modest, this technology opens up exciting possibilities. It can power sensors, remote monitoring equipment, or environmental devices in locations where traditional energy sources simply aren't feasible. Current research is dedicated to enhancing efficiency, discovering more productive microbial strains, and developing materials that improve electron transfer. These bio-based electrical systems illustrate how living organisms can contribute to energy production, complementing mechanical and chemical technologies in truly innovative ways. As we continue to explore this fascinating field, an array of possibilities awaits us. You discover that electricity can arise from surprising biological partnerships. Electric sparks have the power to create new molecules from simple gases. When a strong electrical spark moves through a mixture of gases, it provides enough energy to break existing molecular bonds, allowing for new combinations to form. The intense heat and rapid expansion of the spark create a fleeting environment where atoms and fragments collide with remarkable force. In this brief moment, molecules that typically wouldn't come together can emerge almost instantaneously. Laboratory experiments reveal that these sparks can generate complex organic compounds from basic starting materials like nitrogen, carbon-containing gases, and water vapor. This fascinating process relies on the arrangement of ions, the duration of the electrical discharge, and the surrounding pressure. In nature, a similar phenomenon occurs during lightning strikes, which produce reactive species that can change atmospheric chemistry. Scientists are keen to study these spark-driven reactions to gain insights into both industrial processes and the potential origins of certain compounds on early Earth. The remarkable ability of electrical energy to reshape chemical structures highlights the deep connection between electricity and molecular transformation. As you reflect on this, consider how these interactions play a role in the world around you. Perhaps this understanding can inspire further exploration into the wonders of chemistry and electricity. Imagine a world where water can be sterilized without any chemicals. This is made possible through the application of electrical fields. By using these fields, microorganisms in the water can be inactivated, disrupting their cell membranes or interfering with essential biochemical processes. When a controlled pulse of current flows through a water sample, it changes the electrical environment that surrounds the microbial cells. This sudden shift can cause their membranes to develop pores or create internal imbalances that the cells cannot fix. The beauty of this method lies in its ability to sterilize the water without introducing substances that might alter its taste or composition. The effectiveness of this approach hinges on factors like pulse duration, field strength, and the conductivity of the water itself. Engineers meticulously design systems to deliver precise amounts of energy, ensuring that pathogens are effectively removed while maintaining the water's natural qualities. This technique becomes especially valuable in scenarios where chemical treatments are not an option, or where quick sterilization is essential. It showcases how electrical control can directly influence biological structures, providing a clean alternative for producing safe drinking water. Furthermore, electrical pulses have the remarkable ability to break apart rocks deep underground. By sending high-energy electrical pulses through rock formations, fractures can be created by taking advantage of differences in conductivity and structural weaknesses within the material. Isn't it fascinating how electricity can transform our understanding of sterilization and extraction? As we explore these innovative methods, we invite you to reflect on the possibilities they present. If you wish to continue this journey of discovery or take a moment to pause, the choice is yours. Imagine a powerful pulse coursing through rock, searching for the most conductive paths. This energy focuses itself in specific areas, creating rapid expansions of vaporized moisture and sudden thermal stresses that lead to the formation of cracks. This innovative technique allows for the fragmentation of rock without the need for explosives, minimizing vibrations and disturbances to nearby structures. As an engineer, you have the ability to fine-tune pulse frequency, energy levels, and timing to precisely target different layers or mineral compositions. This method proves invaluable in mining, geothermal exploration, and tunneling projects where accuracy is paramount. Unlike traditional mechanical drilling, electrical fragmentation operates from within the rock, often resulting in cleaner fractures. This process highlights the fascinating interaction between electrical energy and solid materials, reshaping them in a controlled way. It opens up new possibilities for accessing resources hidden beneath the surface. High voltage currents can even sculpt metal with incredible precision. By using controlled electrical discharges, you can shape or perforate metal, removing material with remarkable accuracy. A tool electrode is placed close to the metal, and through a series of rapid discharges, it erodes tiny amounts of material, revealing the potential of this advanced technique. As you reflect on these processes, consider the innovative ways in which technology can transform our approach to resource extraction and material manipulation. Would you like to explore this further, or perhaps take a moment to rest? Imagine a process where heat is generated with precision, creating intricate patterns and fine details without disturbing the surrounding area. The spacing, duration, and strength of each electrical discharge shape the final outcome. This method is invaluable for crafting components that demand complex internal features or extremely tight tolerances. Since it doesn't rely on traditional cutting methods, this technique can shape hard metals that would resist conventional tools. Engineers turn to this electrical approach to produce parts for aerospace systems, medical devices, and precision instruments. The ability to refine metal through carefully controlled electrical interactions showcases the versatility of electricity as a manufacturing tool. Picture electric arcs melting steel in mere moments. An electric arc occurs when current leaps across a gap between two conductors, generating intense heat that can surpass the melting point of many metals. In industrial furnaces, these controlled arcs are employed to melt steel rapidly by directing energy into the material. The brightness and heat of the arc arise from the ionized gas formed between the conductors, allowing current to flow freely. Operators skillfully adjust the arc's length, current, and position to ensure efficient melting and maintain a uniform temperature throughout the furnace. This fascinating interplay of electricity and metalworking opens up a world of possibilities, inviting you to explore further or take a moment to reflect on the marvels of modern manufacturing. Imagine a transformative method that takes scrap metal or raw materials and turns them into molten steel, ready to be refined and shaped. This process is valued for its speed and the remarkable temperatures it can achieve, far exceeding those attainable through traditional combustion methods. This plasma carries both heat and momentum, transferring thermal energy to the material and melting it along a carefully controlled path. As it cuts, the torch expels the molten material, resulting in a clean and precise cut. The quality of this cut relies on several factors, including gas flow, torch design, and current strength. Because the plasma remains concentrated, it allows for swift cutting while minimizing heat damage to the surrounding areas. This tool finds wide application in manufacturing and construction, where precision and speed are paramount. As you reflect on this fascinating technology, consider how it shapes the world around us, enabling the creation of intricate designs and structures. Would you like to delve deeper into its applications, or perhaps take a moment to ponder its impact? Imagine the fascinating world of plasma cutting, where electrical energy transforms into a precise tool capable of reshaping solid materials with remarkable finesse. Consider how lightning, in its raw power, can fuse sand into delicate glass sculptures. When a bolt of lightning strikes sandy terrain, it unleashes a sudden rush of electrical energy that melts the silica grains along its path. As this molten material cools rapidly, it solidifies into long, hollow formations known as fulgurites, which are essentially natural glass sculptures. These unique structures capture the intricate branching patterns of the lightning's channel, extending underground like frozen paths of light. The appearance of each fulgurite varies, influenced by factors such as the sand's composition, moisture content, and the specific characteristics of the lightning strike. Some fulgurites boast smooth inner walls, while others display intricate textures created by trapped gas and the swift cooling process. These natural glass formations offer valuable insights into the intensity and direction of lightning events. Researchers and collectors alike study them to deepen their understanding of how electrical discharges interact with geological materials. Fulgurites serve as a stunning reminder of how a fleeting moment of electrical energy can transform minerals into entirely new structures, capturing a snapshot of atmospheric power in solid form. Would you like to explore more about the wonders of nature? Electric charges play a vital role in shaping the intricate structure of snowflakes. The delicate patterns you see in snow crystals emerge, in part from these electric charges that influence how water molecules bond as the crystal grows. Picture a tiny ice seed forming in a cloud. Water vapor molecules attach to its surface in areas where electrical attraction is strongest. This orientation of charges helps dictate whether the crystal develops into branching arms, flat plates, slender needles, or even more complex shapes. While temperature and humidity control the overall design, the distribution of electric charges adds another layer of intricacy. Even slight variations in the electrical environment surrounding a crystal can lead to significant differences in its form. Imagine crystals growing side by side. As they fall, collisions with other particles can change their charges and influence their further development. The fascinating role of electricity in crystal formation reminds us that even seemingly simple natural objects are shaped by subtle interactions among water molecules, temperature gradients, and electric fields. The atmosphere continually exchanges electrical charge with the ground, maintaining a constant transfer that is part of a larger global electrical circuit. As you reflect on this, consider the beauty and complexity of nature's design. Would you like to explore more about the wonders of the natural world? Imagine a world where the ground beneath you holds a subtle negative charge, while the sky above carries a gentle positive one. This delicate balance creates a downward electric field, encouraging ions to dance between the earth and the air. Dust particles, water droplets, and other airborne elements play a crucial role in this movement, rising and falling in a silent choreography. When thunderstorms roll in, they add an extra layer of energy to the upper atmosphere, intensifying the separation of charges. The entire system